Using the normal distribution to approximate the binomial. The normal approximation to the binomial. The binomial distribution, for reasonably large values of n, resembles a bell-shaped or normal curve. A common demonstration of this fact obtains with a mechanical device called the Galton board or quincunx, which drops balls through a mesh of equally spaced pins. There are a total of n levels of pins. In this diagram there are 15 levels, and at each level a ball has a choice between moving to the right or to the left of the pin. And we can assume that these decisions made at different levels are independent of one another and the balls are all independent of each other, in which case, if we count the number of moves to the right, we expect to have a binomial distribution with parameters n, the number of levels, and p equals 1/2. So for example, in this diagram, if a ball turns right at every level, it ends up in the bin at the farthest right corner. If it's half and half, it ends up in a bin somewhere in the middle, and if it turns to the left on every level, it ends up in a bin at the leftmost corner. This is an example of what's often referred to as a Galton board, or a ball drop experiment, or a quincunx, in which balls are dropped from the top of the board, and they pass through several layers, up to 10 to 15 layers, and on hitting a pin, they determine whether to move to the left or the right. This particular version is found at mathisfun.com. So we assume each ball at the top level determines whether to go left or right, each choice with probability 1/2. And then at the second level, a similar decision is made, left or right, probabilities 1/2. And by the time we get to the bottom of the board, in this case a total of 15 choices, left-right, have been made. The number of those that turned out to be left determines which bin the ball lands in. And you'll notice that the counts of the number in each bin is recorded here, as well as a frequency histogram. And just to convince you of this, I've sped up the process, eventually running to a sample size of around 1,000, by which time the frequency histogram looks very normal-like. Indeed, since there are 15 levels at which each ball makes a decision left or right, and since those decisions are made with probabilities 1/2 each, assuming they're independent of one another, the probabilities of the bins at the bottom correspond to binomial probabilities with n equals 15 and p equals 1/2. What we've discovered is that if a random variable x has a binomial distribution with parameters n and p, and if n is reasonably large, then the standardized random variable, w, obtained by subtracting off the expected value of x minus np, dividing by its standard deviation, the square root of n times p times 1 minus p, the standardized random variable is approximately standard normal, normal 0, 1. And this is simply an application of the central limit theorem. Suppose I define random variables xi, indicator random variables, which take the value 1 if the ith trial in the binomial process turns out to be a success, and 0 if it's a failure. Then the random variable x is the number of successes, and we can obtain that by just summing up the values of xi from 1 up to n. Since the expected value of xi is the probability of success, p, and since the variance of xi is a binomial variance with n equals 1, p times 1 minus p, then a direct application of the central limit theorem says, as n goes to infinity, the standardized random variable, the sum of xi minus np over the square root of np times 1 minus p, approaches the normal 0, 1 standard normal distribution, in the sense that the cumulative distribution function of w approaches the CDF of the normal 0, 1. To indicate this, we'll often write w tilde n 0, 1, which means that it has this approximate distribution, or x is approximately normal with mean np and variance np 1 minus p. Example, a normal distribution to the binomial, approximation to the binomial with and without continuity corrections. Suppose x has a binomial distribution, again n is 20 and p is 0.5. Use the central limit theorem to approximate the probability that x is greater than or equal to 8 and less than or equal to 11. Let's solve this first without the continuity correction. The central limit theorem in this case says that x is approximately normal with expected value n times p, that's 20 times 0.5 or 10, and with standard deviation 2.236 or variance that squared. Let's first solve the problem without the continuity correction, in which case we write the probability x is between 8 and 11. We then standardize, we subtract 10, and we divide by 2.236, the standard deviation, on all three sides of this inequality, ending up with a probability that z is between minus 0.894 and 0.447, where z is standard normal. Again, going to a standard normal table, looking for the value 0.447 and 0.894, we'll determine this probability as 0.4869. Let's repeat this same calculation, but now with the continuity correction. Note that since we're including the values 8 and 11, the probability histogram would include the area from 7.5 to the right and from 11.5 to the left. So we should replace this by the probability that x is between 7.5 and 11.5. And then repeat the same calculation as before, subtracting off 10, dividing by 2.236. Again, getting the probability z is in an interval. This interval is slightly larger. And the value we obtain is now 0.6171. Compare these two answers, 0.4869, 0.6171, a pretty substantial difference. Which one is closer to the true value? Well, of course, the difference is considerable because in this case, n is relatively small, only 20. To determine which one is closer to the true value, we'll have to add up the probabilities of the values 8, 9, 10, and 11. And we get the answer 0.6167. Compare this again with the value with the continuity correction. That was 0.6171. They're very close. In fact, they're close to the first 3 decimals. So certainly if we were to use a normal approximation here, the continuity correction is highly recommended. In general, unless the standard deviation of a random variable like the binomial is less than about 9, using the continuity correction is a good idea and will greatly enhance our approximation. Here's a common problem to determine the appropriate sample size for a poll. Suppose a political party wants to determine the proportion of voting-age Canadians who think Canada should adopt capital punishment. A total of n Canadians are randomly chosen and asked their opinion. And let's let X be the number who answer yes, they do support capital punishment. I'm going to try and guess the value of P, the probability of someone supporting capital punishment, by using the random variable X divided by n. I'm approximating the probability with the proportion X over n in a sample. And I'd like X over n to be close to P. In fact, I'd like it to be within 0.02 units of P. Well, there's always a remote chance that it's not within 0.02 units of P. So let's say it has to be within 0.02 units of P with probability at least 0.95. 95% of the time when I conduct such a sample, I'm within 0.02 of P. Solution. To begin with, n is unknown. For that reason, it's going to be hard to apply continuity correction, but we do expect, in any case, that n will be larger than 50 or 100, and so a continuity correction may be unnecessary. By the normal approximation to the binomial, we know that x is approximately normal, with expected value np, and with variance np times 1 minus p. Now that means that x divided by n is normal with mean p, and with variance p times 1 minus p over n. Now let's write down the condition that we needed to satisfy. The statement that x over n is within 0.02 of p is the statement that x over n minus p is greater than minus 0.02 and less than plus 0.02. But it's unreasonable to expect this to be true all of the time. We're demanding that it be true at least 95% of the time. The probability of that statement is greater than or equal to 0.95. If we do what we did before, subtract the mean off the expected value of x over n, that's p in this case, and divide by its standard deviation, that's the square root of p times 1 minus p over n, and we do that on all 3 sides of this inequality, we end up with an equivalent statement, the probability that z is between minus 0.2 over the square root of p 1 minus p over n and plus the same thing. That probability is at least 95%, 0.95, where z is standard normal. Now look at that right-hand endpoint, 0.02 over the square root of p 1 minus p over n. What this tells me is that the area to the left of that point, under the normal density, must be at least 0.975. Now we've met such a value many times before from a normal table, A value such that the area to the left is 0.975 is 1.96. So 0.02 over p times 1 minus p over n, the square root of that, is greater than or equal to 1.96. Now we have an equation or an inequality that you can easily solve for n. N is 1.96 over 0.02 squared, p times 1 minus p. But we still have a problem. This is the value of n we should use to conduct an experiment whose purpose is to estimate p. We don't know p. The value of n is given in terms of p. So I guess what we could try is see what happens when we plug in specific values of p. For example, let's try p equals 0.3. P equals 0.3 gives us 1.96 over 0.02 squared, 0.3 times 0.7, that's 16.8. If you were to try p equals 0.7, you'd end up with exactly the same answer. P equals 0.4, you'd get a slightly larger value of n. And in fact, the largest value of n you can get in this case with that formula is when you use p equals 0.5. When p is 0.5, you obtain n equals 2401. This is the largest value of n you can get with any choice of p. If we choose n this large, 2401, then we're sure of having at least the required precision in our estimate of x over n, regardless of what the true value of p is. In other words, if we survey 2,401 people, we can be 95% sure that x over n lies within 0.02 of p, whatever the value of p is. Sample size for polls. You'll often read in a newspaper or in the media that a poll is considered accurate to within 3%, 19 times out of 20. This is almost exactly the problem that we've just solved. N individuals are randomly chosen from a large population and asked a question. X is the number in the sample that reply yes. P is the proportion in the population that would respond yes, if asked. And if you look for the number n that must respond so that there's at least a 95% chance that x over n lies within 0.03 of p, so that we can say the poll is accurate to within 3%, 19 times out of 20. That's common expression for with probability 0.95. You should pause and solve this yourself before continuing. This is a similar calculation as we had before. X over n is approximately normal with expected value p and with variance p times 1 minus p over n. The condition we wish to satisfy is x over n minus p is between minus 0.03 and plus 0.03, that to have probability 0.95. Subtracting off the mean, p, and dividing by the standard deviation, the square root of p times 1 minus p over n, we end up with a statement about z, the standard normal random variable. The probability that z lies in this interval should exceed 0.95. This in turn tells us that the right endpoint of that interval must be such that the normal CDF exceeds 0.975 there. In other words, 0.03 over the square root of p times 1 minus p over n is greater than or equal to 1.96. And solving this, we get 1.96 over 0.03, the quantity squared, p times 1 minus p. The maximum value of that corresponds to p equals 1/2, and it's 1067. A sample size of 1067 is adequate for a 3% accuracy, 19 times out of 20. You'll notice we've ignored some rather important issues here, like whether the individuals chosen are independently drawn from a population, and whether all of them responded to the question with a yes or a no. There were no undecideds in this particular poll. And certainly if there were, we would have to increase the sample size.